All right, the last problem that we want to look at is the subset sum problem. So we're going to look at a polynomial reduction from 3CNF SAT to subset sum. So let's talk about exactly what the subset sum problem is. So it takes a finite set of positive integers called S, and then some target integer that's a positive number, and then it asks the decision question, is there some subset of the values, okay, that when you added them all up, they would sum to exactly the target t. Okay. And subset sum is NP complete. We need to prove that. So first of all, we need to show that if we had the subset, that we could verify in polynomial time whether a certificate was correct. So it's very easy to check the answer. On this one, you just take all the numbers in the set, add them up, and then compare it to the target value and see if it's equal or not. Okay, so definitely polynomial in the size of the input. Next, we have to show that subset sum is NP hard. That's a little bit trickier, so we have to choose a known NP complete problem. We're going to choose 3CNF SAT and get a polynomial reduction to the problem in question, subset sum, and show that an instance, okay, that we have a way of mapping an instance of 3CNF SAT, turning it into a subset sum problem, where this will be satisfiable if and only if if there is a subset of the set that we make that sums up to our target. Okay. All right, so let's look at the reduction. So we're 3CNF formula, and it's going to include n different variables and k different clauses. So we're going to look at a reduction algorithm that constructs an instance of the subset sum problem. So we're going to create a set of particular numbers and then a target value that we're trying to reach. Okay. And we have to do that in such a way that the 3CNF formula is satisfiable if and only if we can find a subset of values from the set we construct whose sum is exactly the target that we make. Okay. So a couple of assumptions to make the problem realistic. So first of all, we're going to assume that no clause contains a variable and its negation, because if we had a clause with both a variable and its negation, it would automatically be satisfied by any assignment to its variables. Okay, so that's, we're assuming we don't have something that's always satisfiable regardless of the input. So that's not the kind of problem that we're looking at. Also, we're going to assume that each variable appears in at least one clause. Okay, so if we have variables that never show up, then it doesn't matter what value they have. They can be anything. So they're not very interesting variables. We're only going to consider the ones that show up in at least one clause where the assignment to those variables actually plays a role in the satisfiability of the statement. Okay, so under those conditions, okay, our general outline for this mapping is we're going to end up creating two numbers in the set for each variable and two numbers for each clause, and they're going to be numbers that are in base 10, and they're going to have n plus k digits. So we'll see that's polynomial in the size of the input, and so as long as we can create these numbers in polynomial time, that will be a polynomial mapping. Okay, so how are we going to create these numbers and the target value? Okay, so we label each digit position by either a variable or a clause. The least significant k digits are labeled with clauses, and the most significant digits are labeled by variables. So if we look at the next page, okay, I have an example here that has 3 variables and 4 clauses. So if we label the numbers. So the least significant digits are labeled by the clauses, and the most significant digits are labeled by the variables. Okay, so we're going to create several different numbers, but they're all going to have this same kind of general left to right. So the most significant digits are associated with variables, the least significant digits are associated with clauses. Okay. And then for each variable, okay, we're going to set S the set S will contain two integers, v sub I and v sub I prime. Okay. And each of those has a 1 in the digit labeled by x sub I and 0 in the other variable digits. So let's look at that in the example. Okay. So I have a variable x sub 1. So there's going to be two numbers, one called v1 and one called v1 prime. Okay. And then in the column associated with the variable x1, okay, I have a 1 there, but it's 0 everywhere else. Okay, so v1, sorry, so the x1 only shows up in v1 and v1 prime, but not in any of the other v's. Similar for x2. Okay, x2 has a 1 value, and that place value of the number for v2 and v2 prime, but nowhere else for the v's. Okay, and x3 only shows up in v3 and v3 prime. Everywhere else it's 0. Okay, so those are for the variable. Those are for the variables in the clauses. Okay, for variable 1, that v stands for variable. Okay, 1 for variable 1. v2 has 1s in the x2 position. v3 has 1s in the x3 position. Okay, so that takes care of our two numbers that are associated with the variables. And then we have something similar for clauses. So now if a literal appears in a clause, okay, in its unnegated form, it's just original form, there's going to be a 1 in that place. And if the negation of the literal appears in a clause, then there's going to be a 1 in the vi prime. So let's look at that. Okay, so here's our example. So here's clause 1. Okay, so 1 appears in its unnegated form. So if I go to clause 1 and look at variable 1, okay, it's unnegated, so there's a 1 in v1. 2 appears in its negated form. So if I go down to these two that are associated with v2, okay, well, because it's in its negated form, a 1 shows up in v2 prime for clause 1. And then I have the negated form of x3. And so we have these two things associated with x3. So over in clause 1, because it's negated, it's going there, the 1 is going to be in v3 prime. Okay, so the prime for the negated ones and just the regular one for the ones that aren't negated. Look at clause 2. Okay, it's got x1 negated, so here's my x1 negated. It's got x2 negated, that's going to be the prime for x2. It's got x3 negated, so that's the prime for variable 3. Clause 3 is here. Okay, it's got 1 negated, it's got 2 negated, and it's got 3 in its original. And then clause 4 has 1, 2, and 3. Okay. So that's how we assign. Okay, so we now have chosen how to put 1s and 0s in each place value for all of the v's. Okay. Alright, so that takes care of all the v's. Next, we are going to also, in addition to the v variables, we're going to add two numbers, sj and sj prime. These are called slack variables. And we define them as this, okay, if they have all digits other than the one labeled, they has 0 in all digits other than the one labeled by CJ. Okay, so if you look at S1, for example, okay, it's got all zeros except for in C1. Everything else is zeros. The S2 has all zeros except for the one labeled C2. S3 has all zeros except for the digit labeled C3. S4 has all zeros except for the digit labeled with C4. Well, how do we decide what to put in C1, C2, C3, 4 for the particular S's? Okay, so for SJ, there's a 1 in the CJ digit, and there's always a 2 in the CJ prime digit. So notice, okay, for S1 and S1 prime, it goes 1, 2. Okay, so the regular one is a 1 and the prime is a 2. Same thing over here for S2, we've got a 1 and a 2. 1 for the regular, 2 for the prime. For 3, it's only in the C3 spot, but it's 1 for the regular and 2 for the prime. Again, for 4, 1 for the regular, 2 for the prime. Okay. And then we also have a T value. This is the target that we're trying to make. And there's a 1 in the places that are associated with the variables, and there's 4s in all of the places associated with the clauses. So the target number that we're trying to make is 1, 1, 1, 1, 4, 4, 4, 4. So depending on the number of variables and the number of clauses, we'll have a number of 1s followed by a number of 4s. Okay. So each of these is interpreted as a base 10 number. Okay, so these are our various numbers. So this number would be like 1,000,001. This number would be like 1,110,000. So these are the numbers that go in our set. Okay, so we now have a mapping from a 3 set to a set of numbers. Okay, so our set of numbers, we've got, you know, each row of these represents a number. And we've got a target value down here that we are trying to see. Are there a subset of numbers from here that will add up to this target? And we will need to convince ourselves that if this is satisfiable, we'll be able to find numbers that add up to the target. And if it's not satisfiable, we won't be able to. Okay, so one thing to note is that the greatest sum that you could ever get in any position is 6. So notice you have 1, 2, 3, 4, 5, 6. Okay, so if I added up all the numbers, the maximum I could ever get is 6. So if I were to if I chose every single number in here, okay, each position could only ever add up to 6, so I would never have any carries, so I don't have to worry about carries. Okay, so now let's convince ourselves that if this is satisfiable, then I can find numbers from here that add up to the target that I'm trying to make. Okay, so let's suppose that we do have a satisfying assignment. Okay, well, then it must be the case that we can't have, you know, both of these being 1s. Only one of them can be, because if we have a satisfying assignment, we can't have both a variable and its negation being true at the same time. At most one of those, if we have a satisfying, exactly one of those will be a 1. Okay, so any subset that I choose will include either this one or this one based on whether or not this one is satisfied or that one is satisfied. Sorry, whether I have an assignment of 1, whether the original variable is true or whether its negation is true. Okay, so I'll choose the value to go in my set based on whether the 1 came from V1 or whether the 1 came from V1 prime. Okay, so that's how I will choose this between V1 and V1 prime, between V2 and V2 prime, and between V3 and V3 prime. Okay, so I look at whatever one is 1 and I include that in my subset. Okay, So because each clause is satisfied, the clause contains some literal with value 1. Okay. And each digit labeled by a clause has at least 1 contributing to its sum by the values in S prime. Okay. So I know that each clause, at least one of these has to be true. So if I have 2 of them true, then I might have 2 of them. If I have 3 of them true, I might have 3 of them, but I might only have 1. So depending on how many of them evaluate to true, I might get, at most 3 or at least 1 of the values from my V1, V2, and V3. Okay, and so whatever I don't get, and I need to make up for the 4, I can choose, S1 and possibly S1 prime as well to force the sum to go up to 4. So if I only have one of these that evaluates to true, I would choose both S1 and S1 prime. If I have 2 of these things that have truth assignments, okay, then that would only add up to 2, so I would add S1 prime, and that would make it add up to 4. If all 3 of the variables in my clause evaluated or the literals evaluated to true, okay, then I would only choose the first one, the non-prime one, to make it add up to 4. Okay. So, and because there's no overlap between that place and anything else, it's only going to contribute to that particular clause. It's not going to add to the sum in any of the other clauses. Okay. All right. So that is how I will choose the values that are going to go into the subset. Okay. And so now that I've chosen those values to go in the subset, if I have a satisfiable statement, I'm guaranteed to be able to add up to my 1, 1, 1, 1, 4, 4, 4, 4, 4. Okay. So for the example, let's look at that. So if I have a satisfying assignment of the negation of x1 is true, the negation of x2 is true, and x3 is 1. Okay, and so if we looked at, for example, clause 1 and 4, they contain exactly one of those. Okay, so here's clause 1. Okay, so it doesn't have an x1 bar, right? We can see it doesn't have an x1 bar. It doesn't have an x2 bar, does it? No, it does have an x2 bar, and it does not have an x3. Okay. So it contributes 1 to the sum in that spot. Okay. If we look at clauses that contain 2 of the literals, they're going to contribute 2. 3 of the literals will contribute 3. Okay. And as we said, we just then choose the slack variables to make everything else add up to 4. Okay. So if we have a satisfying assignment, I can definitely choose a subset of these to add up to the required target. In a similar way, if I can find a subset that adds up to the required target, well, then I just go and I make the truth assignments according to what I see here. So if I had a subset that added up to the target where V1 prime was chosen in my subset, well, then I would know that I needed to make X bar be equal to true. And if I had V2 prime, then I would know that I needed to make the X bar 2 be prime, and so on and so forth. Okay. Alright, so that's what I was just saying. So if I have a subset that sums up to T, you have to include exactly one of those 2, and you just make sure that, if that variable is in S prime, then you set xi to 1, and if the prime one is in there, you set the negation of x to 1. Okay, so that's really tricky. Who knows if you or I would have thought of that as really slick. But we have a way of mapping a satisfiable statement, so a Boolean formula, into a set of numbers, okay, where we can have ask ourselves if a subset of those numbers adds up to the specific target. All right, so there are many other NP complete proofs that we could go through, but these are the only ones that we are going to look at just because we're out of time. So you should understand all of those reductions and be able to do reductions for the different problems we looked at, and I won't require any other ones for you to look at.